In the last class we discussed hashing. We saw a few collision resolution techniques. So we first saw chaining, then in the last class we saw double hashing, linear programming. We also did a little bit of analysis of these collision resolution techniques. Right. In today we are going to talk about trees. After we are also going to look at binary trees and see some data structures for trees. So what is a tree? So many of you might have come across a tree before, except that this tree is going to be different from the ones that you came across before, right? So here the root will be at the top. Most trees that you see around you, you don't see the root. So the root is going to be at the top of the tree. So in this tree, A is the root. There is a notion of parent and children. So the node B is the parent of node D and E. Okay? By the same argument, A is the parent of B and C. C is the parent of F, G and H. A is a parent of B, which in turn is a parent of D and E. So A is an ancestor of D and E. A is also an ancestor of F, G and H. A is also an ancestor of I. Right? A is a grandparent, sometimes we use the term grandparent. A is a grandparent of D, E, F, G and H. Yeah, you understand what the difference between ancestor and grandparent is. D and E are descendants of A. Yeah. In fact, B, C, D, E, F, G, H, I are all descendants of A. C and B are siblings because they have the same parent. B is a sibling of C, C is a sibling of B. G and E are not siblings. G and E are not siblings, please note. F, G and H are siblings. D and E are the children of node B. Right? So, A is a parent of B, B is a parent of D and E are children of B and C are children of A. All of these are descendants of A, as are all of these. I has three ancestors, H, C and A. H is the parent, C is the grandparent and A is the great grandparent, although we do not use that term and we just call it an ancestor. Okay, so the terms we had defined till now were more in the nature of a family tree. So now we will come to real trees, right? And then D, E, F, G, I are called the leaves of the tree. So this is the root. So if you just turn it upside down, then this should be the leaves, right? The extremities. So what is a leaf? A leaf is so these I also called, the generic term for these are also nodes of a tree. So a leaf is a node which has no children. Right? If a node has no children, it is a leaf. So H is not a leaf, H has a child, but I, F, G, E and D are nodes which do not have any children and so they are leaves. More definitions. A, B, C and H are called internal nodes. Right? A node which is not a leaf is called an internal node. Okay, now we associate a notion of level with each node. The root is at level 0. Children of the root are at level 1. The children of those nodes which are at level 1 are at level 2. Right? So D, E, F, G, H are all at level 2. Right? It is not just that H is at level 2, all of these are at level 2 and this is at level 3. Sometimes we also use the term depth. Right? So depth and level are the same thing. So this is depth 0, depth 1, depth 2, depth 3. The height of the tree is the maximum level of any node in the tree. So what's the maximum level of any node? It's 3. So the height of this tree is 3. Any questions till this point? The degree of a node is the number of children it has. B has degree 2, C has degree 3, H has degree 1. The leaves have degree 0 because they have no children. Yeah. So basically, basic terminology, quite intuitive also. Any questions? No. So what are trees used for? They can represent the hierarchy in an organization, right? So for instance, there is a company, let's call electronics. Electronics are used, which has some divisions. R&D is one division, sales is another, purchasing is another, manufacturing is a fourth division. Sales, there is, let's say, domestic sales is one subdivision of this division, and international is another one, and so on and on, right? So you could represent the organizational structure through a tree. You could also use a tree to represent the table of contents in a book, right? So you have, let's say, a book called Student Guide, which has chapters on overview, grading, environment, programming, support code. This then has, maybe this chapter has some sections called exams, homeworks, programs, whatever, right? They could have some subsections and so on. So that would just build up the tree. Your file system in, if you use the Unix environment or even the Windows environment, is also organized as a tree. Yeah. So this is the, let's say, one root directory of a certain directory. These are two subdirectories in that. Okay. And then within this subdirectory, I have some other subdirectories, and within them I have some homeworks and assignments and whatever I have. Yeah. So your file system is also organized like a tree. Okay. So more definitions. So much of today's class would be about definitions, and then we'll start using these definitions in later classes, but you should understand them, and if there is any doubt of any kind, please ask. An ordered tree is one in which the children of each node are ordered, right? So what does that mean? That means that this is, we'll call this the, there is a notion, right? We would like to put this child to the left of this child. Right? Suppose you want to draw a family tree. In a family tree, maybe you want to draw the eldest child to the left, right? And the younger child as we move from left to right. Right? So there is a notion of order there, and sometimes you want to reflect that order in your tree. But there would be no notion of order, let's say in your this example, right? Well, this is a directory. There are two subdirectories here. Now, whether I place this to the left of this or to the right of this doesn't really make a difference as far as the picture is concerned, right? And it doesn't convey any additional information. But sometimes you might have the notion of an order between the children's. Right? Such a tree is then called an ordered tree. A binary tree is an ordered tree. Right? So there is a notion of a left child and a right child. Actually, it's an ordered tree in which every node has at most 2 children. Right? So this is an example of a binary tree. This has 2 children. This has only 1 child. This has only 1 child. This has no children. These are leaves. So we have 1, 2, 3, 4, 5 leaves, which have no children. This node also has only 1 child. Right? And these are ordered, so there is a notion of a left and a right. If I were to change this, if I were to draw this on the left and this on the right, then I get a different binary tree. It's not the same binary tree.
So that will still be a binary tree?
That would still be a binary tree, but it would be different from this binary tree.
But once we have defined the notion of some order, once we interchange the top 2 nodes, so how will it still remain ordered? Won't the order be distorted then?
No, so this is one binary tree, All we are saying is this is one binary tree, and if I were to draw it in a slightly different manner, which means I put this, I move this entire piece to the left and this entire piece to the right, then I get a different binary tree. Right? There are two different binary trees. That's all we are saying.
So different if we, even if we took the file system example, if we change the top two subfolders which we had for the root, if we flip them across, then also we'll get different. So is it necessarily that it depends upon the situation which we are using?
Yeah, all of this is dependent upon what application you have. This is just a way of representing information, right? Sometimes the order is material, it has meaning to it, sometimes it has no meaning to it. When it has some meaning to it, then we would rather use an ordered binary tree, and when therefore if you were to change the order, then you are representing something different, because then you have changed the order. Yeah, we will see more examples of this and then things will become clearer. Perhaps. I can also define a binary tree in a recursive form as follows, right? A binary tree, I could say a binary tree is just either a single node, a leaf, or it is an internal node, which is the root, to which I have attached two trees, two binary trees. This part is called the left subtree and this is called the right subtree. So I can construct any binary tree in this manner. Yeah, I take a node and I attach a left subtree and a right subtree. And how do I get the left subtree and the right subtree? Recursively. That itself is obtained by taking a node and attaching two left and right subtrees. Right? I've said and or, which means I might, this left subtree might be null. I might not attach anything here. Or I might not attach anything to the right. Or I might attach both. Okay? So remember this term, we have introduced two other terms, left subtree and right subtree. This is called the left subtree of this node. Yeah? And this is called the right subtree of this node. What is the left subtree of this node? It would be this piece here. That would be the left subtree of this node. Okay, more examples of, examples of binary trees, arithmetic expressions, right? I have an arithmetic expression which looks like this. I can represent this as a binary tree. What does that mean? Well, this is, so let's look at a parenthesization of this expression. And so suppose I have parenthesized it in this manner. So we have 4 plus 6. So the numbers here will be the leaves of my binary tree and the internal nodes would correspond to the operations. Right? So in fact, this is one way you could evaluate this expression also. Right? You would take this thing, 4 and 6, you would sum that. Right? So you would draw a tree which has one internal node and whose two children are 4 and 6. And this internal node would have the plus operator in it. And whatever is the resulting value, we are adding that to 1. So I draw a tree whose root is a plus operator, whose one child is 1, and the other child is the subtree that I obtained from this operation, and so on, and I could build this tree. Right? So this is just a way of representing, another way of representing this arithmetic expression. Yeah? Decision trees are another example of binary trees, right? So this is an example that I taken from a book. So much of it would not make much sense. Maybe Starbucks and Cafe Paragon, you've not come across them, but nevertheless, suppose, what's a decision tree? Each node in the decision tree corresponds to some decision you have to make, right? So whether you want, so you come to the top root node and you ask whether you want a fast meal. If the answer is yes, then you come to this node, whether you want a coffee or not. If the answer is yes, you go to Starbucks. If the answer is no, you maybe go to some other place, right? And so on and on. So decision trees are another example of binary trees. Why binary? Because typically it's yes and no. Right? So you would follow this decision tree and get to a particular node. Okay. So this was just more of terminology and examples, right? So let's get to some more concrete stuff. Let's define a complete binary tree. right? So we're still at binary trees. So as you can see, every node in this tree has less than or equal to 2 children, right? At most 2 children. But I will call such a tree a complete binary tree. Why is it a complete? Well, so we call a tree a complete binary tree if at the ith level there are 2 to the I nodes, right? In some sense it's full. And every node has 2. No. That is not equivalent, right? Every node has 2 children. Saying that every node has 2 children doesn't give you a complete binary tree. Okay, let's see if I can quickly show you why not. Let's see this. Does every node have 2 children? Every internal node have 2 children in this tree?
Not saying every node, not necessarily internal.
Oh, every node has 2 children, then a tree has to have leaves, right? So it cannot be the case that every node has 2 children. Some nodes have to have no children. So yeah, so just the requirement that every node has 2 children, every node other than the leaf, that means every internal node has 2 children, doesn't imply it's a complete binary tree, and this is a counterexample to that. Every internal node here has 2 children, but this is not a complete binary tree. Right? So here is an example of a complete binary tree. So we want to say at level I there are 2 to the I nodes. So this was level 0, 1 node, level 1, 2 nodes, level 2, 4, level 3, 8. Right? Okay. Now if h is the height of this tree, this example, what is the height of this tree? 3. Recall, height was the maximum level number. So don't count this as 4, count it as 1, 2, 3. Yeah? If h is the height of the tree, then that means all the leaves are at level h. Yeah? If the leaves are all at level h, then in the definition of a binary tree, we have said that level I has 2 to the I nodes. So that means that there are 2 to the h leaves. So the number of leaves in a complete binary tree of height h is just 2 to the h. Right? What is the number of internal nodes that we have? Well, at level 0 we have 1 node, level 1 we have 2 nodes, and so on. So this is this sum 1 plus 2 squared all the way up to 2 to the h minus 1, right? Because at level h all the nodes are leaf nodes. So it's this sum which is 2 to the h minus 1. Right? Okay, so this is the number of internal nodes and the number of leaves is 2 to the h. So the number of internal nodes is the number of leaves minus a 1. Right? This is for this complete binary tree that we are talking about. For a complete binary tree, number of internal nodes is number of leaves minus a 1. And so what is the total number of nodes in this tree? It's 2 to the h, which is the number of leaves, plus 2 to the h minus 1. Yeah, which is the number of internal nodes. So it becomes 2 to the h plus 1 minus 1. Right? Let's call this number n. So if I have a tree of n nodes, if I have a complete binary tree of n nodes, then what is the height of this tree? Or let's go one step at a time. What's the number of leaves in this tree? So if this is n, so number of leaves was 2 to the h. So 2 to the h equals n plus 1 by 2, right? Just from this expression. So the number of leaves in a complete binary tree on n nodes is n plus 1 by 2. So if I have a complete binary tree on n nodes, roughly half the nodes are leaves, and the remaining half are internal nodes. And similarly, I can say that if I have a tree on n nodes, then the height of the tree is log of the number of leaves. Why? I can evaluate h from here. Its h will be n plus 1 by n plus 1 log of n plus 1 by 2, and so it's just the log of the number of leaves. Right? Or you can go directly from here. Number of leaves is 2 to the h, and so h is log of n, log of the number of leaves. Sorry. Any questions on this? So just some simple counting that we are doing here. Yeah. So, but you should be able to say that if I give you a tree of height h, what is the number of a complete binary tree of height h? What's the number of leaves it's going to have? What's the number of internal nodes it has? If I give you a complete binary tree on n nodes, then what's its height, and so on and on. So if you have a tree on n nodes, then its height is log of n plus 1 by 2. Right? That's the height of this tree. Right? And the other thing that you have to keep in mind is that in such a tree, the number of leaves is very large. It's roughly half the total number of nodes. Yeah, so it's a very leafy kind of a tree. Okay, now what's a binary tree? So that was a complete binary tree, right? But a binary tree, we said, is any tree in which every node has at most 2 children. So what you can do is you can take a complete binary tree, or to get any binary tree, you can start with a suitably large complete binary tree and just cut it off, right? So for instance, here, if I were to cut off this piece and this piece, then I would get such a binary tree, right? And I can always do it, no matter what tree I wanted, right? If I had any, if you said take this binary tree of height 3, then I would start with this complete binary tree of height 3 and just cut off some pieces to get this thing. I can always do that, right? And this picture is a proof. Is everyone with me? So let's use this fact that you can obtain any binary tree by just pruning off a complete binary tree. Take a complete binary tree, cut off some pieces, cut off some branches, and you'll get a binary tree. So if I have a binary tree of height h, then in a complete binary tree at level I, they were exactly 2 to the I nodes. So in a binary tree at level I, there will be at most 2 to the I nodes. There cannot be more than 2 to the I nodes, because a binary tree was obtained from a complete binary tree by pruning. So this is an important fact. At most 2 to the I nodes at level I. And if there are at most 2 to the I nodes at level I, this implies that the total number of nodes in your complete binary tree, in your binary tree of height h, is at most this. 1 plus 2 plus 2 square, which is this. Yeah, it's height h, so the last level is h. At level 0, there will be 1 node, but at level 1, there is at most 2 nodes. At level 2, there are at most 4 nodes, and so on. So this is the maximum number of nodes that a binary tree can have. So let's rewrite this. Suppose I told you that the tree has n nodes, right? So then n is less than or equal to this quantity. So n is less than or equal to this, which means that the height of the tree, I just rearranged this, is greater than log of n plus 1 by 2. Right? So if I give you a binary tree with n nodes in it, its height is at least log of n plus 1 by 2. And there is a particular binary tree which achieves this equality, and that's the complete binary tree. Right? So think of the complete binary tree as the tree which acquires the smallest height. So if I create binary trees with a certain number of nodes, the one which has the shortest height will be a complete binary tree. Right? Because there you are packing all the nodes as close to the root as possible by filling up all the levels to the maximum. Right? So that's the minimum height of a binary tree. I give you a binary tree on n nodes, its minimum possible height is this quantity, roughly log of n. Right? What's the maximum height that a binary tree on n nodes can have?
n minus 1.
Right? And so a binary tree on n nodes has height at most n minus 1, and this is obtained when every node has exactly one child, and this would be a picture of that. Right? Yeah. So every node has exactly one child, and this could be zigzagged in any manner, and the height here is 1, 2, 3, 4, 5, 6, 7, 8. There are 9 nodes here, and its height is 8. So that's the maximum height of a binary tree. So binary tree on n nodes, minimum height is log of n. Log of n plus 1 by 2, whatever, but let's just say it's log of n. Maximum height is n minus 1. That's a mistake many people make. They always assume that binary tree means height is log n. No, it could be anywhere between log n and n. How many leaves does the binary tree have? Right? What's the minimum number of leaves it can have and what's the maximum number of leaves it can have? Let's figure that out. We'll prove that the number of leaves in a tree is less than or equal to 1 plus the number of internal nodes. In any binary tree, the number of leaves, this is a useful inequality. Number of leaves is less than 1 plus the number of internal nodes. Or at most, the number of leaves in a tree can be 1 more than the number of internal nodes. How will we prove this? We'll prove it by induction. Induction on the number of internal nodes. Okay. So base case, consider a tree with only one node. If a tree has only one node, how many internal nodes does it have? 0, because that one node doesn't have any child. So that's a leaf. So base case is when number of internal nodes is 0 really, in which case the left hand side, the right hand side is 1 and number of leaves is 1, so the inequality is satisfied. So we will assume that the statement is true for all trees with less than or equal to k minus 1 internal nodes. Right? So this should actually read as statement is true for trees with at most k minus 1 internal nodes, not just k minus 1, but anything even less, this statement is true. So we will not prove it for a tree with k internal nodes. So suppose I have a tree with k internal nodes, right? Let's say on the left subtree I have k1, k sub 1 internal nodes. Then how many internal nodes do I have on in the right subtree? If in the left subtree I have k sub 1 internal nodes, then how many nodes do you have, internal nodes I have in the right subtree? Exactly k minus k1 minus 1, right? Not at most or any such thing, because all the internal nodes are either there in the left subtree or are there in the right subtree, or it's the root node, right? So the minus 1 is because of the root node. So this is the number of internal nodes in the right subtree. Now let's apply a induction hypothesis. K1 is less than or equal to k minus 1, and this quantity is also less than or equal to k minus 1, right? So we can use the induction hypothesis that the number of leaves in the left subtree, which has k1 internal nodes, the number of leaves is less than or equal to k1 plus 1, and in this subtree the number of leaves is less than or equal to k minus k1 minus 1 plus a 1, which is k minus k1, and the total number of leaves is just the sum of these two. All the leaves are either in the left subtree or in the right subtree, nowhere else. So the total number of leaves is just the sum, which is k plus 1, which is what we wanted to prove, right? Since we started off with a tree with k internal nodes, so we have to show that the number of leaves is less than 1 plus k. Yeah, is this proof clear to everyone? It's a simple proof which shows that the number of leaves is at most 1 plus the number of internal nodes. Right? There was a tree we saw where the number of leaves was equal to the number of internal nodes plus 1 in a complete binary tree, right? What was the number of leaves there? The number of leaves was 2 to the power h if h was the height of the tree, and the number of internal nodes was 1 plus 2 squared all the way to 2 to the h minus 1, which is 2 to the h minus a 1. So there was exactly a difference of 1 between the number of leaves and the number of internal nodes, right? So the complete binary tree once again achieves this equality, right? For any other tree, the number of leaves will only be less than or equal to this sum. Right? How small can it be? So let's look at that. So for a binary tree on n nodes, the number of leaves plus the number of internal nodes is n. Yeah, because every node is either a leaf or an internal node. And we also just saw that the number of leaves is less than or equal to the number of internal nodes plus a 1. Right? So, I will just rearrange this. This implies that the number of leaves is less than or equal to n plus 1 by 2. Right? What have I done? I have just number of internal nodes is greater than or equal to number of leaves minus a 1. So, I replace that here, and so I get that the number of leaves is less than or equal to n plus 1 by 2 for any binary tree. So, that is another thing that to keep in mind. In any binary tree, the number of leaves will never be more than half the number of nodes in the tree, never, right. And again this equality was achieved for our complete binary tree. That is the most leafy tree, yeah. All others are drier trees, let us say. And the minimum number of leaves that a tree might have is just 1. Right? And what is the example for that? The same example I showed you before, that the tree on 9 nodes had only 1 leaf in it. So, now let us look at an abstract data type for trees. So, you would have generic methods which you have seen for all the abstract data types till now, right. So, these are generic container methods. So, size, how many nodes are there in the tree, whether the tree is empty or not, and elements is a method which lists out all the elements of the tree. You can have position based container methods. So, the kind we saw for the list or the sequence data type, right. So, swap elements p and q, I specify 2 positions p and q. So, think of the positions as references into the tree, except that using the position data type I am not able to access anything else but the element sitting at that position. Yeah.
So, what does positions do? It tells the data at that.
The positions, the method positions will specify all the positions in the tree. It will give you all the positions in the tree as a sequence.
Positions
so that
along with the data.
Just the position, the position objects. This positions method has no parameters, right. When you invoke it on a certain tree, it will just give you a sequence of all the positions in the tree, references to all the nodes in the tree.
Each node has a certain data assigned to it.
Once you access a particular position, then you can, using the element method on that position, access the element in that node. Swap elements p comma q, given 2 positions p and q, you are swapping the elements at these 2 positions. Replace element p comma e, which means that given a position p, you are replacing the element at that position with e. Query methods, given a particular position, is this the root of the tree? Yeah. Given a particular position, is this an internal node? Given a particular position, is this external or leaf? Sometimes you use the term external, sometimes you would say leaf. Yeah, is this position, does this position correspond to a leaf? Accessor methods, root. When I call root now, it will return to me a position of the root, an object of type position, right. So, what you understand the difference between this and this. Given a position, is it a root? And this returns the root.
The position of the root?
The position of the root.
So, the position of the root means a reference to that particular
Exactly.
node.
The position of the root means the reference to that particular node, except that this is not a reference to the node, but it is a reference of type position, so that you cannot access anything else but the element in there.
The same thing the typecasting which we did.
This was the same as the typecasting we did earlier. Yes. Parent p, given a particular position, return to me the parent node. Children p, given a particular position, return to me the children of this node. Right?
Will it return the children or the position?
Okay, now what will it return? If children, there could be many children of a certain node. So, how will it return the various children?
Sequence.
As a sequence. It will return all the nodes It will return a sequence, an object of type sequence, which will contain the positions of all the children.
But then shouldn't the XSI method give us the information the data inside it?
That can be invoked on the position. Position has an element method which will let you access the data. The update methods are typically application specific. This would be the generic method for a tree. Okay, binary tree should really be treated as a subclass, as a derived class from a tree. So all we need to do is to continue to have the same methods as we described for a tree, but have some additional methods now. Right? There would be a notion of a left child. Given a position, give me the left child. Give me a right child, or give me a sibling. Right? We'll come to these update methods when we see examples of these. So I'll skip that for now. What is the node structure in a binary tree? Right? What are the kind of data that you would be keeping in an object corresponding to a node of the binary tree? You would have data, you would have a reference to the left child, you would have a reference to the right child, you would have a reference to the parent typically, yeah, and you would also have a reference to key or data associated with this node. Any element that is sitting in this node, you would have a reference to it. Right? These would all sit in here.
So where is the position of the node itself? It has the reference to the parent and the child.
Yeah.
But where is the reference to itself stored?
The reference to this node will not be stored in the node. That doesn't make any sense. Right? So for instance, if I accessed this node, suppose this was the root node, and I used the root method to get a position to this node, then using that position I can now access the left child by invoking the left child method, and in this manner I can get the position of any node, right? And once I have the position of a node, I can then invoke element method or whatever I need to do to get the data associated with that node.
So sir, a node is implementing the position interface.
A node in this case would definitely implement the position interface, exactly. Right? So this is what a binary tree would look like if you look at the links and so on. This node, its parent link would be null because it has no parent, it's the root node, right? And then it would have a left child. The left child would be referring to this node, the right child would be referring to this node, and so on and on. Right? This does not have any right child, so its right child member would be referring to null. Any questions? Okay. Now that was for a binary tree. Now how do we take care of arbitrary trees? Let us say unbounded trees for now. Right? So this node has, let us say, 3 children. This node also has 3 children. So are we going to have 3 different data members here for the to refer to the 3 children? Right? So that's not clear how to do it, because then if it had 4 children, then how would you create space for another member, and so on and on, right? So the way to do it is that you have a reference to one of the child only, right? And then all the children are in a linked list. Okay, and each children will have a reference to the parent. So all of these children would be pointing to this node. This would be pointing to only one of them, which would be the head of this linked list. Yeah. So from this node, if I want to refer to the children, I can just come here and essentially return all the elements of this linked list. How do I know I have reached the last element of the linked list? When the next is empty. Why does the first field of this denote empty? Because it does not have any children, right? So every node now still has only 3 members, 3 data members, right? Parent, or 3 references, one for the parent, one for the leftmost child, and one for the sibling, for the right sibling, right? So this would refer to only its leftmost child, not to all the children, because that we do not know how many there are. and it will have one more to refer to the right child, to the right sibling, right? Because for this it has to refer to the right sibling. Yeah. Is there any question at this point? Some confusion? So you can do with only 3 references.
So will the left node always point to the left child in the last one, in the bottom which one?
This one,
Left node is pointing the right one.
this one,
The left node is pointing to the right child.
this one. Yeah. So this had only one child, right? It had only one child, so it's just pointing to that one child.
There is no sense of left and right.
There's no sense of left and right here then. This is not a binary tree. Left and right only makes sense in a binary tree, remember. Right? So actually I should not have written left child here. I should write first child or some such thing. Yeah? Or any one child. It just points to any one child, and that one child then lets you access its siblings through a linked list. Right? So from that first child you'll go to next child, and to from there to a next child, and from there to a next child, and so on. So you can step through all the various children through a linked list. Any questions on this? So with that, we'll end our discussion on binary trees today. In the next class, we are going to look at traversals of trees, and yeah, that's all.